Thanks a lot. And thanks a lot also to the organizers for the opportunity to speak here. I'll talk about some work I've been looking into with Youssef since I joined his group at MIT. And it's the first time speaking about this, so all the more exciting. Density estimation via measured transport. So I want to start on a more general note than just density estimation, which is, something everyone in the room knows that, I mean, in statistics data science, we often have to deal with complicated probability distributions. Not always clear that our goal is actually to estimate the density. You know, we might want something different from this distribution of interest. We might want to generate samples from it, right? So there's kind of these two categories of goals one could have. One is to approximate this distribution of interest pi by some estimate that's close in some distance. The other one might be that I want to generate samples z such that the law of these random variables z is close to my distribution of interest, right? And in different settings, I might have access to different things in order to accomplish these goals. So for instance, in density estimation, classically, I'm just giving samples, given IID samples, say, from pi, and from those xi, I build a measurable function that estimates pi. The same is true in generative modeling, even though in generative modeling, I'm not necessarily interested in, first, one should always be interested in having a good estimate if one wants to, generate more samples. But the ultimate goal here is to, make more replica samples from whatever distribution is underlying the data set at hand. Now, there's this whole other category where pi is not necessarily, this unknown distribution of my data set, but it, say, arises as a posterior distribution. And so here, what I have access to is quite different, right? So here I might be able to evaluate pi up to normalization constant, or I might be able to, take gradients of the log density. This is the case, for instance, in Bayesian computation or in sampling, right? And of course, for all of these tasks, there are classically established methods that do these things in Bayesian computation, for instance, notably MCMC, density estimation, especially in the non-parametric statistics literature. There's things like wavelets, KDEs that achieve minimax rates and do very well. And however, I want to focus on a class of methods that's based on transport, right? And this has received quite a lot of attention in recent years. What is a transport map? Well, it's actually very simple. It's just a map, right? That is able to couple two distributions. If you specify some reference, you can just take the push forward or pull back if S is invertible of this reference, right? And so then you can go between eta and pi simply by going back and forth via S or S inverse, right? So this is kind of a basic observation that you can express complicated distributions pi via reference and a map, right? So say pi is your distribution of interest, then you kind of want to couple it to some simple tractable distribution. So typically what people use are, for instance, standard normal distributions. Here, since I'm gonna do theory and I want to focus kind of on the simpler case of bounded domains, think of a uniform on a bounded domain, right? So if you're able to find an invertible map S that pushes the target pi into eta, then you can do these tasks that I was saying before kind of almost automatically. So you get a density estimator just by the change of variables formula, right? So here the upper hash means it's a pullback. So this is just kind of the dual of this here. So you get an estimator for pi just by kind of whatever map S you've learned, and you pull the reference back under it, which means you have to kind of, and this is just change of variables formula, right? It's like a plugin. And what comes for free additionally, which is perhaps not as obvious in classical methods in non-parametric density estimation, is that you can actually very easily generate samples, so long as you can generate samples from the reference right? Which, if it's tractable, should be feasible. And then you kind of just push these samples through the inverse of S, and you'll get samples from the target pi. Okay, so here's just an image of, you know, kind of this isotropic, nice Gaussian density being transformed by this map S to some target that is non-log concave and, you know, more complicated, not as straightforward to sample from or to express. Okay. Okay, and now it turns out that, you know, there's a lot of ways to actually couple references and targets, right? So we think, when we think about transport, maybe probably first and foremost about optimal transport, about endowing the space of probability measures with a Wasserstein metric, and then looking at maps that kind of realize this Wasserstein cost, right? So this is Brainy's theorem. So Brainy maps are just one category of transport maps one can look at. So what does Brainy's theorem say? Well, under mild assumptions so say if you have densities which are supported on convex domains, then there exists kind of this unique map that is a gradient of a convex function that realizes the Wasserstein cost. The Wasserstein cost is defined as an infimum over the transport cost over all couplings of eta and pi. And Brainy's theorem says that you can just simply integrate over pi and look at how far each point x gets displaced by this optimal transport map, right? So that's an optimal coupling. That's one way to link these two densities. Now, there are other methods too, right? Like intrinsically from a statistical viewpoint, it's not necessarily clear that you always want to go for a Brainy map, right? You might want to go, for instance, for Knothe-Rosenblatt maps, which is actually what I'm going to focus on for most of the talk. These maps have a certain structure. They're triangular in the sense that the first component map only depends on the first variable, and until the last variable, the last component map is allowed to depend on the full x vector. I'm gonna go into more details regarding this in a bit. And for one dimension, you know, these maps are equivalent, right? So optimal transport maps are actually also monotone and just given by the composition of one CDF with the inverse of the other CDF. And now there's a whole other class, you know, they're given by flows. So here we're just looking at kind of deterministic mappings. X gets mapped to another point, but actually, especially in machine learning methodology, there have been a bunch of kind of time-dependent flows, where at time 0 you're at the distribution of interest, and time 1 you're, say, at a normal. These are called normalizing flows, and you can invert these flows, right? So sometimes they're described an ODE, or PDE, or SDE, as Andrew was telling me yesterday at lunch. And if you can invert it, then you can say you can run ODE backwards. So often that's convenient. Then you can go from the normal back to the target and generate samples, for instance. Okay.
Later showed that this optimal transport is realizable by a flow. Right.
Yeah, by the Wasserstein. Yeah. Right. So okay. So I want to say a few words about what's been out there. So a methodology has been developed for a while, notably in Yusef's group. Early on, they looked at kind of was like sampling and like transport methods as a surrogate for MCMC, or as an alternative to MCMC. And then recently there's been a lot of work on normalizing flows to be used in variational inference, again sampling, or generative modeling. Okay, and then on the theory side, there have been a bunch of things, but it's been fairly sparse, to be honest. So there's some work by Jakob Zech about approximating high-dimensional triangular maps. So typically in high-dimensional statistics, if you want to do sampling using transport, you would things would be high-dimensional, and you can use sparse polynomials or ReLU networks to approximate these triangular maps. The works that's closest to what I'm going to present is this kind of statistical consistency work in a very recent paper this year that kind of shows just some statistical consistency for density estimation using triangular flows. Okay. And then I put a bunch of other papers that are not super related to our work, but they relate to transport. So, and I'm sure I'm missing a lot, so apologies for that. So there's some work by Philippe and his student on estimating optimal transport maps given kind of input-output pairs. If you assume already that you know the smoothness of the transport map, right? And then also density estimation, Wasserstein distance, which I'm not going to do. I'm going to look at density estimation in more classical metrics like Hellinger or L2. But yeah, this is very cool work. Okay, so for most of the rest of the talk, I want to focus on these triangular maps, just because they're kind of more tractable than Brownian maps. But I'm going to comment later on how this links to other classes of transport. So what are these Knothe-Rosenblatt maps, right? So given a pi and a eta, you can always construct a map of this form that that's triangular in the sense, and that's kind of partially monotone, meaning each component is strictly monotonically increasing in the last variable, right? That couples these two densities, right? So the pullback under this map of eta is equal to pi, and this map is unique up to variable ordering. So of course they're kind of de factorial such maps depending on how you order the variables, right? And it allows for an explicit construction as opposed to OT maps actually. And this class of maps kind of closed under inversion. So inverses of KR maps are again KR maps, and notably also the determinant of the Jacobian is very easy to evaluate, right? Because the determinant of the Jacobian is going to be lower triangular, and so it's just the product of the diagonal derivatives if you want. So this is computationally very attractive, and that's why, for instance, these are the building blocks also for these autoregressive flows used in machine learning. So these are actually maps that people use. Okay, and so I'm going to focus on density estimation. So say I have very classically, on the unit cube, a sample given from some P0, and this P0 has a Lebesgue density that I model in some regularity class. Okay, and then what people do in practice is they actually they look at this. I mean, the way they motivate it is they view this whatever class of transport maps curly S they have, they kind of try to minimize the KL between the underlying distribution and this variational family given by the class of transports, right? But of course, you don't know P0, especially in the density estimation setting. So you approximate it kind of by this empirical sum given your samples, and these are going to be similar if xi come from P0. Now, of course, in the setting here, this is just maximum likelihood estimation, right? Like in sampling, it would be different if you're kind of trying to numerically compute this thing, and this P0 is a posterior, but that's kind of what people always try to do. And in density estimation / generative modeling, it turns out to be kind of maximum likelihood estimation. You have a question?
Again, sorry.
Eta is the reference distribution. Like a uniform, say, or like something tractable, and the complexity kind of lies in the class of the S's, right?
So this is, as you're saying, like maximum likelihood, that you're defining a class of densities and you're maximizing the likelihood for it.
Absolutely.
But it's defined through the collection of the S's.
Absolutely.
Okay.
Yeah, that's exactly right. So the question, of course, is how should you pick S, right? Like if you start with a regularity assumption on P, that's kind of somehow going to propagate to S. And that's key to understand, right? To pick an appropriate class such that you don't underparameterize or overparameterize, etc. Right? So one thing that's well known is that if the reference and the target are alpha smooth, possess some differentiability properties, then so is the KR map going to as well, right? So this is actually quite immediate from the definitions almost, at least on the Helder scale. Now, so basically what you could say then, okay, so say I want to model then, I want to model a density that lies in this alpha smooth class, and we have like a lower bound and an upper bound, right? Say my P0 comes from this M class. Well, then a sensible thing to do is to kind of take this MLE over this S class, which is kind of all the properties that we'd want from a triangular map, being bijective, triangular, monotonically increasing in each map. Yes?
Slow this morning because
no worries.
the dinner last night. But on the last slide, let's go back to the last slide. So is it clear that this argmin doesn't just give you sort of basically the Dirac measure at all the points? I mean,
well, it depends on the class S, no? Like in nonparametric.
I mean, here S is not constrained at all, no? I mean, so now on the next slide you put in some
S and S.
It's some class.
Ah, okay, so it's some subset of this. Okay, I see.
To be
not
chosen.
taking the argmin over all. Okay, sure.
Right, yeah. But yeah. I mean, first of all, these two have to be kind of diffeomorphisms. Otherwise, this, like this change of variable formula, doesn't hold anymore. So in which case you, for instance, always get a density as the pullback density. Yeah. No. Okay, so for instance, one sensible choice to you kind of take this alpha smooth class of KR maps that's slightly bulky to write down, but it's just saying that essentially, right? And then you kind of get this initial result. You can use theory from M estimation that Sarah has developed and others, but you've already done all the work. To say that the Hellinger, is the red dot actually visible? It's very kind of weak. Okay, so you here get the minimax rate of estimation that corresponds to an alpha -1 smooth target, right? And this is just an upper bound, so I don't actually know whether over this class, this is also a lower bound. But I'll tell you the reason why this is the case that one gets alpha -1. Well, basically, we said when everything is alpha smooth, then S is going to be alpha smooth. Now you can ask the other way around, right? You can say, well, if S is alpha smooth, and which is the class I'm optimizing over, and if eta is alpha smooth, what is the regularity of this pullback? And there you'll lose 1 degree of regularity, right? So, and if this is the class, in the end, what's going to determine the convergence rate is kind of like the bracketing metric entropy for the class of all pullbacks. And if all you can say about the regularity of that is alpha -1, then this is the price you're going to pay, right? So in some sense, grinding on minimax rates kind of comes down to taking a closer look at the regularity properties of these KR maps, right? And one thing that I then realized was, well, actually, what would be ideal is if the KR maps were actually alpha +1 smooth, right? Then you just take them and you're in business. However, the answer kind of lies in between. So they're definitely alpha smooth, but they're also not alpha +1 smooth. They kind of have an anisotropic regularity, which comes from the construction, which is unfair because I didn't tell you the construction, but it is kind of like a, well, if you think in 1D, then there's no anisotropic regularity because there's only one direction, but but then the optimal transport map is going to be given by the composition of the CDFs, right, which are one smoother than the densities themselves. Now this doesn't hold in general dimension, but it kind of only holds along the diagonal because the Knothe-Rosenblatt map is kind of based on iterating this construction conditionally on the previous variables for the last variable. So that's where this anisotropic smoothness kind of comes from. And then you can show that actually here you get this sharp correspondence, at least sharp in terms of, level of regularity. So what does this say? So it says that all the maps that are coupling alpha smooth densities are contained in this anisotropic class, and vice versa, all the pullbacks of eta under maps in this class are again alpha smooth. Okay? So this now goes both ways, whereas previously it didn't. Right? And so once you have this and you do proof as before, then you get the minimax rate for alpha smooth densities for this pullback again estimator. And yeah, it's it's still employing the same kind of machinery for maximum likelihood estimators. Now, okay. So these are kind of the initial result. Yeah.
Slow. It's not because of wine. I'm always slow.
Because of the
It's not because of the wine. I'm always slow. So when you say that the eta factorize, so you want somehow to restrict to the isotropic case, because in the anisotropic case you had a problem, but you know that isotropic case you are able to have the alpha plus 1 degree of smoothness, right? Am I understanding that?
I think the eta you want to factorize just because I actually think one might be able to show it without eta factorizing, but because of this kind of weird composition structure, you want to make your life easier by choosing you can choose your reference as you like, right? For
That's
instance,
not isotropic, it just factorizes, no?
it's just
Yeah, so
you
it's
can even
reverse,
choose your
yeah.
eta to be smooth, right? Like it's only the targets that you have no control over.
Okay.
Yeah.
Thank
So
you.
this is more like a technical assumption, yeah. Okay, but in reality,
If you have a product measure like the uniform, aren't these triangular maps just going to be the inverse CDFs of the conditional distributions of that variable from the earlier variables?
yes.
So you can, as soon as you start talking about properties of their derivatives, you can just think about, I'm making assumptions about those smoothness properties of the conditional densities of the class I'm taking maximum likelihood over. So if you look at it that way, it all becomes more familiar.
Absolutely, and I think it actually becomes very, like it very naturally fits into what we know.
Yes.
Yeah.
Okay.
Yeah. Okay. So these results were kind of over for maximum likelihood estimators over these weird non-parametric classes, right? The set of KR maps are a convex set, but they're not even a convex cone in the case of bounded domains because you have this weird range constraint, right? So what people do in practice is they actually almost never optimize directly over it, but they parameterize transport maps or flows, via some other parameters. So in some sense, they take they take some theta indexing a family of diffeomorphisms, right? So what I want to show now is just kind of a more general theorem that really kind of just also tells what's under the hood. So say you have a more general class of diffeomorphisms indexed by some index theta, and you possibly also want to do penalization, because penalization is actually numerically much more convenient than doing maximum likelihood over a high dimensional class. And so here you have kind of this more general objective, which is here again just the likelihood of the push forwards of the pullbacks, and here you have you just have some complexity penalty on theta. Right.
From the previous setting very quickly to a parameterized setting, but could one do what you talked about before with a penalized version?
Yes, this comes out of here as well. Yeah. But this is kind of more because I haven't done this, but in mind I have things like you want to parameterize this using neural networks, or you want to like you want theta to be network weights, or you want so in some sense you want to set it up in this very general setting, but yeah.
So usually, if you consider, you would use a Hilbert space penalty instead of a C alpha penalty, no? So where's
yes, and actually, I'm going to show this with Hilbert space with like Sobolev penalty. Yeah, this is the one example I wrote out in the yeah. So kind of in line with this previous observation that kind of the diagonal derivatives play a special role for triangular maps. The theorem actually holds also for non-triangular maps, but I want to stick with triangular. Okay, so we kind of need the C1 diagonal norm, and then just adapting what's really known from M estimation, thanks to Sarah and others. What we can write down are kind of these kind of important quantities. So the second one being the metric entropy integral of these classes of transport maps that essentially have penalty smaller than R, right? That come from the parameter theta. And you need to cover these in this anisotropic norm. Okay, in practice, this is actually, once you write down concrete parametrizations and stuff, this is actually easier than one might think. Right here, it looks a little bit strange, but this is the crucial norm to bound. This is the right one to bound. And if you have control over this metric entropy integral, then you can kind of get a concentration inequality for the push forwards, right? So what do you get? So basically, this delta here is constrained to be larger or equal than the entropy integral divided by square root n, delta squared, right? And this kind of determines the variance of your empirical process. And then here you kind of the theta star. Oh yeah, I didn't tell you what that is. That is just any element, but you can think of it as the best approximation from the model in Hellinger, but also in terms of the penalty. So these two first terms here are kind of like the bias, right? And so this underlies everything. One of the key differences here is that you're kind of operating for the coverings, you would typically operate on the level of the theta using the penalty, whereas previously for the MLE result, what we did was we were directly bounding the bracketing metric entropy of all the push forward measures. So we're not operating on the space of the transport maps themselves, but really on the space of the densities. So and this actually gains you quite a lot, similarly as in nonlinear inverse problems, actually, because because this parameterization from the map to the pullback is nonlinear, so it kind of behaves weirdly. But okay, and so now I want to give one example.
Same in all three occurrences of this theorem. There's this constant.
Well, well, I took the constant to be the maximum of three constants because the result is kind of monotonous in each of the
certainly not monotonous. It's an interesting statement, but
well, not monotonous. I don't know how to say this well. If it holds,
it's monotone in C, so you can take the maximum.
If it holds for one C, it holds for all larger C's. And if that is true for all three C's, then you can just take it to be the maximum, right?
Any constant should do them.
Very monotonous.
So you make the probability, the C in the probability statement, if I replace it by 2C, then your bound is also twice as large.
Sure. That's right.
It's correct.
Oh, right. Yeah, I'm just saying there exists a C such that this holds for all n. Yes.
He could have used the
right,
C1,
right.
C2, C3. He was trying to be nice.
So it's true that the constant grows in a way that it might not have to, but it's still correct.
It is still correct, which is what what I was going for the slide. But in the paper, I'm not sure. I disambiguate them. Maybe I should. Okay. Yeah. Okay. So I told you why one might want to use this more general thing with reparameterizing using theta. So here's an example how one might like parameterize these weird maps, right? So essentially there's three things one tries to enforce. You want triangularity, you want this monotonicity, and the third one is arguably the strangest one, which is a range constraint, right? Which necessarily already tells you that you cannot, this is not a linear space, right? Because the linear function spaces, even on arbitrary domains, have unbounded range, obviously. So you need some kind of construction which goes like this. So you take So f here is kind of the linear parameter, right? That can be taken to be, say, any function on the unit cube. You put it into a link function that kind of forces you to be positive, the composition of the two, and then you integrate in the last variable, right? And one thing you can omit, and I would argue that is actually quite a natural construction. The thing that is slightly artificial and that people do not do in practice is this kind of renormalization to really enforce the map to be bijective onto the unit cube, right? But here you have to divide kind of by the line integral over the last variable. Okay, and then using this construction, you can kind of go from any function f on the unit cube to a map that is a KR map. This parameterization is not unique, however. Like you run into identifiability issues potentially, right? It's like not clear that it's unique, but which is actually why penalization then actually becomes really important, right? So I mean, this is just a lot of notations, but what is essentially means this f is this kind of triangle Sobolev space is just functions on the unit cube that are triangular, where each component is Sobolev alpha on the k-dimensional unit cube. Okay, and then you can use this as a penalty norm, and you can just kind of do this Tikhonon regularization over f and optimize over f. And because I've already written down kind of two convergence rate statements, I didn't want to write the details for this one. But essentially, this also gets the minimax rates, which relates to Richard's question. Of course, you could also penalize directly on the set of KR maps, right? But I don't know if one really wants to do that. So I would argue that this linear reparameterization is somewhat more natural.
Assembly depends on the dimension.
Yes, badly. I think a priori badly. Yeah. Mostly because of the product structure in the determinant. But maybe one can improve this for certain cases. But that's why I think it's it will be
Sorry, this result now is for what is the assumption of P0 now?
Oh, it's again alpha smooth. Sorry.
C alpha.
C alpha, log, and upper bounded. Yeah.
But you don't have any.
I think H alpha is enough. So, I'm not. Yeah, probably for and alpha large enough. Alpha larger than D. If you take H alpha, I think you need alpha large enough so that things become multiplication. Sobolev spaces become multiplication algebra.
But I was gonna keep my question right until the end, but you're not using mixed smoothness results, like some sort of anisotropic decaying. Yeah, not at all.
Well, the kind of fun, that's a very sharp observation, because here the funny thing is kind of that this map is it changes the smoothness, right?
Yeah.
But in an anisotropic way, and it matches exactly this diagonal smoothness thing. So if you take f to be an isotropic smoothness Sobolev function and you plug it into this construction, it's gonna have the right anisotropic smoothness that you want, which exactly means that also it's actually convenient that on the level of f you can penalize using the isotropic smoothness. It's kind of simultaneously.
My question was more related to, you said it depends badly on this constant depends badly on dimension. But if you have some assumption on the smoothness in the density that you try to approximate, then
absolutely.
This is, for example, in the paper of Zech.
Yeah, that's what I was going to ask. How does it relate?
It's right. Yeah, I agree. I haven't looked at it, but I would be very nice. Yeah. But yeah, for instance, if as you both say, if P0 lies in some like density class with respect to a Gaussian that compactifies in high dimensions, for instance, right? But okay, so there are a few remarks regarding the results we have. So you can also do wavelet discretizations, or choose theta to be wavelet coefficients, or other basis expansions. This is going to be a part of the paper as well. And maybe more importantly, so this general theorem that I showed you, you can replace everywhere where there was this diagonal norm, you can replace by just like the C1 norm, which is a stronger norm, right? Because you have to take into account the full Jacobian matrix. Then you can do this actually for general, also non-triangular classes. You could optimize, for instance, over the space of Brenier maps. If you can suitably understand their regularity properties, which I think is challenging, but and also on more general domains. And what's ongoing is actually some work with Jakob and with one of the students in Yusef's group, where we transfer this kind of statistical consistency stuff to ODE setting where there's a time component, possibly also neural ODEs, where this is something people do, where you parameterize the flow field of the right-hand side in the right-hand side of the ODE by a neural network. Okay, so I mean, I already mentioned, I mean, I think this direction would be really cool. There are people in the room who I think know much more about optimal transport than I do. And I'm really interested in looking at this. I already mentioned neural net representations as well. And I think there's a lot of open questions. And I think it's kind of a really nice class, really natural class of methods. And there's a lot of interesting stuff to be done there. So thanks a lot.